Hello, welcome back to CS700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. So let me recall the topic from last session and then discuss about the new aspects for today. So last time we talked about computing on basic spaces, and the main example of basic spaces are the Cantor space of infinite sequences, binary sequences, and the Baire space of infinite sequence of integers. And I'd like to call these base spaces because for these, it's kind of immediate how to define computation on them, namely operating on sequences of bits or operating on sequences of integers. That's what a Turing machine, that's what a while program is kind of designed for. So there's no need for further definition. Subtlety arises when we want to talk about computational complexity, namely since such computations involve infinite output and maybe even infinite input, we cannot really measure the computational cost in dependence on the length of the input, as is customary in the discrete theory of computing. So there n is usually used to denote the binary length of the input, but here instead we use n to denote the binary length of the output. And since the computation runs indefinitely, will produce an infinite string of output bits, we measure the time, the number of steps it takes until the nth element of that infinite output sequence arises. And this output sequence may be an infinite sequence of bits in case of Cantor space, or maybe an infinite sequence of integers in case of Baire space. And the requirement for computing a function like here is that the bound, the running time bound, and number of steps made until the nth output bit appears must not depend on the input, which is superficially kind of strange and very different from the discrete theory of computation. But again, please keep in mind that the input are infinite anyway, so we cannot assign a length to that input. More subtle is the question of why can we even obtain such running time bounds that do not depend on the input. In the discrete case, there are only finitely, exponentially, but finitely many inputs of length n. But here, we in general have infinitely many or even uncountably many possible infinite binary strings or infinite integer sequences as input. And so although the computation may halt for every single such input, it's not at all clear and actually in general even wrong that the computation admits a running time which does not depend on the input. So in the discrete setting, if the computation terminates for each of the exponentially many inputs of length n, we can take the maximum of these finitely many running times to obtain a running time bound which depends only on the length n of the input, but not on the actual input itself. But here, when the inputs have infinite length, even if the computation is finite for every single of these inputs, it's not at all clear whether we can simply take the maximum of these running times, because that would be a maximum over infinitely many running times, which may easily be infinite. And here's such an example. So consider the following function. So input is an infinite binary sequence called U, and let's consider the case where this sequence contains at least one occurrence of a digit 1. So this is going to be a partial function. It is only defined on input strings u, which contain at least one occurrence which is not 0, one of the elements. And then we can ask, how long is the initial consecutive number of zeros in this string? So if this doesn't start with 0, then the length initial sequence has length 0, right? But if it starts with 0, then maybe the next element is also 0, and so on. So we can ask, what is the length, what is the number of initial zeros in the infinite sequence argument u? And the function is defined as follows. If this number is odd, then the function value should be an infinite sequence of ones. If the number of initial zeros is even, then the function value should be an infinite sequence of zeros. Okay, that's our function. And observe that this function is computable. It's a simple algorithm that indeed just scans the number of initial zeros one by one until hitting the first non-zero element, and then looking whether this number is even or odd. And if it is odd, then start outputting switch modes, start outputting ones and never end. Whereas in the other case, start outputting zeros and never end. And as you can see, this algorithm correctly computes this function, but the running time of that algorithm cannot be bounded independently of the argument, because the number of initial zeros may be arbitrarily long, and this algorithm thus may take an arbitrarily long, finite, but arbitrarily long time to scan and count the number of initial zeros, right? So this algorithm will keep scanning and counting these zeros. And also recall that the function is partial. So if the input is actually just zeros, there's no occurrence of 1 at all, then this function is undefined, function value. And that is also reflected by the algorithm. In this case, the algorithm will keep scanning and scanning forever and never be able to determine the number of infinite zeros, because that's infinite. And nor will it be able to detect whether this number is even or odd. Infinite is neither even nor odd. And so the algorithm will never switch to its second phase where it outputs any of these. So 2 observations from this example. First, this is an example where the running time cannot be bounded independently of the input. So the time it takes to output the nth output symbol is mostly governed by the time it takes for the first case to scan the number of initial zeros, and that is just unbounded. And second observation, this algorithm is only a partial algorithm, because the underlying function is also only partial function. The domain of that function and the domain of that algorithm is not compact, and that will be important later on this slide, because last time we proved 4 important properties about computing on base spaces. So the first property is that any computable function, possibly partial, from counter space to counter space, if it's computable, then it must necessarily be continuous, which again can be kind of expected, since we already know the same to be true and necessary for computing over the reals, right? So this seems to be maybe a more general phenomenon, not necessarily related to the real numbers, computing over real numbers, but also computing over counter space, and actually also similar argument over bare space. So the argument, the proof to those 2 statements, counter space and bare space, is actually very easy and similar to the proof that any computable real function is continuous. Uh, we suppose the function is not continuous, and then we kind of fool an algorithm claiming to compute such a function by running it twice. First, uh, on an argument right at the discontinuity and observing the behavior of the algorithm, and then uh, restarting the algorithm to run at an argument which is sufficiently close such that the algorithm has not yet been able in its previous finite number of steps that the algorithm is actually different. And this is even simpler to do here in the Cantor case, where if the algorithm has made t steps, then it could have been only looking at the first t elements of the input sequence. And so any changes that we in our proof, in our thought experiment execution, any change we make to the argument infinite binary string beyond the tth element will remain undetected by the algorithm during its when we restart it for the first same number t of steps. So that's a brief idea for the proof of the main lemma A. And the main lemma B says that if a function on Cantor space is computable in time t, then t is a modulus of continuity of that function from into Cantor space. And the proof to that is basically, again, what I've just said. Observe that in time t means that the algorithm can have made only t steps until producing the nth output symbol. And within these t steps, it can have looked at most at the first t elements of the t of n elements of the argument string. So if we restart the algorithm and secretly make some changes to the argument beyond the tth element, the algorithm will not be able to notice and will perform the same computation as previously, and in particular output the same first n symbols, and any difference in the output can happen only at the n plus first symbol, and this is precise to the definition of having modulus of continuity t on Cantor space because of the very way we define the metric on Cantor space, as you can see here. So that's item B. And before stating item T, let us recall this function, which reflects the number of steps that the algorithm A makes on input U until having output the nth element. And this function, by its definition, depends on the argument U, whereas we are interested in a function that counts or bounds the number of steps made until output of the nth output that does not depend on the argument U. So we want to kind of define this to be the maximum over this here for all possible U. And as I said, the all possible U, that's a very dangerous thing to say because there are uncountably many such U's in general. But the third statement of the main lemma says that this function's dependence on U. So if we fix the algorithm and if we fix the number n of output symbols that we're interested in, finally many of the infinite output, then the dependence on the first argument, infinite string input, is a continuous dependence, which in view of the particular metric on the space of inputs is the same as saying that it is locally constant. So put differently, whenever this number here, the number of steps is finite, whenever the algorithm A takes a finite number of steps before an argument U before outputting the n symbol, then this finite number, same argument as in B, provides a bound for us in our thought experiment. If we change the argument U beyond that number T that the algorithm has made so far, then the algorithm will not be able to even detect that and therefore perform it exactly the same way as previously. And in particular, make the same number of steps before producing the same end symbol for output. So that this function is locally constant, and that means it is continuous. In general, again, this is a partial function if the algorithm fails to produce the end output symbol on some infinite binary strings as argument u. Um, but if this function is a total function, or put differently, if the algorithm is total, it produces the end symbol after some finite time for every single possible argument u, which means the algorithm computes the function. And if the domain of that function is compact, then it follows that the algorithm has a time bound which does not depend on the argument u. Namely, we can calculate mathematically the maximum of over all these finite running times with a maximum over all, ranging over all, possibly infinitely many input sequences u. And the reason for that is simply just mathematical fact that every continuous function on a compact domain is bounded. And by item C, we have seen that this function is continuous in this argument. And the hypothesis of item D says is that the domain must be compact. So compactness of the domain is an important property that will occur frequently throughout the rest of this lecture, and particularly when we talk about computational complexity, which we've already started by defining it here. Okay, so that's the recap from last time, and we ended by discussing compact subsets of our basic spaces. The compact subset of Cantor space is just every closed subset. That's obvious. But since Cantor space itself is compact, but bare space is not compact, so some effort is needed to characterize the compact subsets of bare space, and this actually has been achieved and is well known. The classical Koenig's lemma characterizes when a subset of bare space is compact, namely two conditions. First, it must be closed. That's of course necessary. And secondly, if we consider the set of its finite initial segments. So this is a set of infinite sequence, and we take all finite initial segments of various lengths of elements in that set of infinite sequences. And if that set is finitely branching, if and only if it is finitely branching, then the original set is compact. And to illustrate the notion of what it means to be finitely branching, Cantor space as one subset of bare space is indeed finitely branching because every node has finite, more precisely has two children. But in general, when we talk about bare space, of course, then every node has in general, more than two children. For instance, this child could be numbered, labeled with 2. This was labeled 3, and so on. Every node, when we talk about bare space, every node will have all integers as label for its children. So every node has actually infinitely many children, and this is not, the node is not finitely branching. Finitely branching means every node has finitely many children. That's the definition of being finitely branching in a tree. And this is known to be sufficient and necessary together with being closed for a subset of bare space to be compact. Bare space itself is not compact. So I'm not gonna prove the Koenig's lemma, but we're going to apply that. Maybe now we want to talk about computing over other spaces, over spaces which are not basic spaces. And as in the discrete theory of computation, other spaces are encoded over basic spaces. So classically, for instance, spaces of graphs are encoded either over finite sequences of bits or over finite sequences of integers with emphasis on finite. And similarly, when we want to talk about computing on spaces of continuum cardinality, such as the space of real numbers, the space of continuous function on some fixed compact subset, or the space of compact subsets over some uh, closed space X, then uh, we encode these over basic spaces. We encode the elements of these spaces as infinite binary sequences or as infinite sequence of integers. And the, this infinite sequences, the space of infinite sequences is uncountable. It has cardinality of the continuum, which is matches the cardinality of the set of real numbers and the cardinality of the set of compact subsets and the cardinality of the space of continuous functions, because all these spaces are basically separable. So that's how we define uh, generically computing over spaces of continuum cardinality by encoding these spaces by encoding its elements as infinite sequences of bits or infinite sequence of integers. And this intuitive notion of encoding is formalized with a notion of being a representation. That's terminology from Klaus Neuhaus' classical book on computable analysis. A representation of a set X is a surjective and partial mapping from a base space, Cantor space, or Baire space onto the space X. Onto meaning it's surjective, and that reflects mathematically that we want every element in the codomain in the space X under consideration to be the image of some element from the basic space, from the domain of this representation, to be the image under some U. And if um, U is mapped to some element X, then we're going to say this is a Xi name, U is a Xi name of X. Where Xi, we need, of course, to include reference to the representation. So if we consider different representation of the same set of the same base space, then the notation changes. Things will become names of other elements or will become names of nothing at all, because this is a partial mapping in general. So some elements may not have names, um, and in general, we don't require that the representation that the function be injective, which means in general, every element has several names, and actually it will turn out that for a reasonable theory of computation, every element will necessarily have infinitely many, even uncountably many names. So that's terminology. Um, And let's now consider some example representations, some examples of how to formalize encoding and computation over some uncountable space, some space of continuum cardinality beyond the Baire and Cantor space. And our main example space is, of course, a space of real numbers. And for real numbers, we had, on an intuitive level, we had several ways of defining computability, which I'm happy to recall here for your convenience. So one of the equivalent notion was to say that the real number under consideration that has a decidable binary expansion, meaning a Turing machine or a while program can, when given a input some index, some integer of the binary expansion, can decide whether this bit of the binary expansion is 0 or 1. So that was one of the definitions. But remember, we had other definitions, several definitions, and our second definition was by means of approximation. So let's say that the real number under consideration is the limit of a rational sequence, a sequence of fractions, numerators and denominators being integers, a sequence with error bounds that converge, although here slowly, to the actual number, So the error bound must tend to infinity to zero. And here we, for convenience, we fix a particular rate of growth or rate of attenuation, namely 1 over n. It was our second definition, and we proved initially that both definitions are equivalent, although we had to consider different cases, infinitely many cases of binary expansion, finite binary expansion, infinitely many cases, all cases of dyadic rationals. And then we proved that both notions are actually equivalent, and we also proved them equivalent to a third notion, namely outputting a sequence of dyadic rational approximations. So here the approximation are just ordinary rational numbers, fractions, and here they are fractions whose denominator is fixed to be 2 to the n, where n ranges over this, the space. So, right, and remember that we proved all three to be equivalent, but for part of the equivalence proofs, you had to consider different cases, and it was difficult, if not impossible, for an algorithm to find out which case it was currently in. So instead, we were forced to take care of it and obtain a non-uniform proof. So now let's turn these three notions of computability of real numbers that we've just recalled into encodings of real numbers, into representations of real numbers, at least for the unit interval, representations and encodings that use as codomain the space of infinite sequences. So for the binary expansion, it's kind of natural how to define that. Namely, recall the binary expansion is just a binary sequence, a sequence of zeros and ones, because that's how we define Cantor space, right? So whereas for the rational encoding, the rational approximation, we would involve fractions, that is pairs of integers, which are here now conveniently described interleavingly into a sequence of integers, right? So the even numbers come up and the odd numbers are down in the fraction. So that this notion actually refers to Baire space. Namely, this is an infinite sequence of elements from Baire space with certain property, of course, which I'm not going to go into further. But the baseline is that in this conception, we're going to see that a representation in this sense, an encoding of the elements of this space, is going to be actually unbounded. It's going to have non-compact domain. We'll see that later. And the third, encoding the third representation that arises from this equivalence here is by numerators of dyadic rational approximations. So here we have general rational approximation, here we have dyadic rational approximation. Also here we deliberately choose approximation error bound 2 to the minus n for reasons that will become clear much later in this lecture, not today and not even in this month. So to summarize, we've recalled the computability notions of computability for single real numbers from earlier lecture, and we have kind of turned them into representation, that is, into formalizations encoding sequence of binary, how to encode elements from other spaces over infinite binary sequences or over the Baire space of infinite integer sequences. And the formalization then gives rise to such a representation for the binary encoding. I'd like to call this representation beta for binary. So beta is a partial function from, actually it's a total function from Cantor space onto the unit interval. So here we're restricting to the unit interval for convenience purposes. The rational representation is actually a mapping from bare space onto the unit interval because it will receive as argument a certain sequence of numerators of rational numbers and will then force them into alternatingly into the numerator and denominators of the fractions that are supposed to approximate the given real number up to R1 over n. Right. So here we really need the full power of being able to encode integer sequences or sequence of integer pairs that are here kind of loosened up as consecutive elements of one single sequence of integers. And the third representation arising from this third notion of equivalent notion of computability of single real numbers, again, a representation of a bare space because it kind of takes as argument an infinite sequence of integers, and that's just these integers an. Okay, so that's a way of formalizing as encoding of previous ad hoc notions of computability, and you will soon see criteria that allows us to further distinguish these three, for now, representations. Namely, they turn out to have distinct properties, and one of them will be used as the canonical representation of the unit interval throughout the rest of this lecture. Okay, so these were representations over the first one over the space of counter space of sequences of bits, which we can also consider as a closed particular subspace of the space of bare space of integer sequences. But the other two are at least a priori encodings over bare space of integer sequences, right? Here we have one integer sequence where with an alternating elements from the sequence we take as numerator and denominator. But by recoding these integers in binary as finite binary strings, we can recover and turn these representations over bare space into representations of a Cantor space, right? By just concatenating the elements of that sequence in bare space and turning that into a concatenation into an infinite sequence in Cantor space. So, and in the rest of this lecture, we're going to move back and forth between both pictures, encodings of a Cantor space and encodings of a bare space, because for now, computability theoretically doesn't really matter, doesn't make a distance. Only later when we talk about computational complexity, then it's going to become very crucial. What is our underlying ground space? Okay, so for now, our underlying ground space is Cantor space or bare space. And now if we have such a space like Cantor space or bare space, or in other space X equipped with a representation in this sin, then we can now define what it means to compute a function finally between these spaces. Namely, to compute such a function is going to be defined in terms of operating and manipulating names of arguments and names of values. So let me illustrate that, but first here's a formal, maybe two formal definition, namely a realizer of a function from x to y. When x is a space equipped with representation xi, and y is a space equipped with representation epsilon. So now it makes sense, right? Then we define what it is first to be a realizer of that function. A realizer is go ahead and replace, at least in your mind, the numbers and arguments to the function under consideration. Replace these by by names, right? By xi names, and similarly replace the values or function values by names of the values. So Here's a picture that illustrates that. I'm going to explain that in more detail. So here we have a commutativity diagram. What you see on top are the function and the spaces we're interested in. Namely, we're considering function which is totally defined as function from the space x to the space y, and computing this function when the space x is equipped with this representation and the space y is equipped with this representation, then computing such a function um, is defined in terms of computing a realizer, and a realizer is just something that makes this diagram kind of commutative, right? So we have here these two representation, and the realizer, by definition, completes this diagram, makes it commutative, now that it uh, gives the same result whether we proceed in this way or this way. And that's captures intuition behind the definition of being a realizer, psi epsilon realizer in this case, where psi and epsilon are arbitrary but fixed representation that we will need to refer to throughout the when we talk about computation on such represented spaces. And the same, we can again recode the function realizer as a transformation from and to Cantor space, and we can equivalently consider it as a transformation from and to Baire space. This is actually more general, um, right? Because Cantor space is a subset of Baire space. And computing a function is meant to mean computing psi epsilon realizer in the below sense. And notice that the realizer F is indeed a transformation on and from Cantor space to Cantor space, or on and from Baire space to Baire space. So that has already been defined. And now this definition in yellow extends our definition to computing from basic spaces to computing over more general spaces, represented spaces. So how does it relate to our previous notions of and definitions of what it means to compute, let's say, a real function, which should be a special case of this rather general theorem or definition in yellow? And recall that it means to compute a real function, partial function, right? Um, means to convert any sequence of numerators of dyadic approximations to the argument to a similar sequence of numerators of dyadic approximations to the value f of x. And this is the definition for what it means to compute a real function. And since we're already here, we're going to generalize that and also consider the case of computing a real multifunction, which you can see here, indicated by the double arrows from the codomain to the domain. Double arrow here means that this is a multifunction, that the value of that return value of that function can and may in general depend on how the argument is encoded and beyond the argument itself only. And as you see, this is actually consistent with our new definition, which it must be, otherwise there would be a issue of well-definedness. Namely, this is exactly the definition of what it means to delta compute a function, a real function or real multifunction, where delta, as you recall, was this representation of real numbers, or at least the unit interval, over Cantor space. So our classical definition of what it means to compute a real function or multifunction actually is equivalent and generalizes in the way I've just explained here to computing over arbitrary represented spaces. Okay, now let me mention two further details. So first, I promised to talk about this restriction thing. and the restriction. So this symbol means that the left-hand side is supposed to be a restriction of the right-hand side, and restriction here for now means that it is the domain of the left-hand side, it be a subset of the domain of the right-hand side. But remember that we also discussed about another more general notion of restriction, namely restricting could also mean extending, actually enlarging the codomain, enlarging the set of possibly admitted return values. So we use this definition and the notion of restriction here for a good reason, because remember that we indeed are talking about multifunctions here. Um, but also let me point out that the realizer is and must be a single valued function. So even if we're realizing a multifunction, then we still require that the function under consideration be actually functional and not a multifunction, because all models of computation that we considered so far are actually functional. If they get restarted with the same argument again, then they will produce the same value. So that's also sometimes called um, uh, deterministic computation. Okay, so and yeah, this this important property that we allow restriction and not just equality, um, that is a reflection of this no, property, this part of the definition of what it means to compute a real function. Namely, we explicitly allow the function to behave arbitrarily. It may even return a value, even though the argument does not belong to the domain. And that's why we allow this to be a restriction rather than just plain equality. Okay, good. So moving on, why is this a reasonable definition? Why is it reasonable to define computation of a function or multifunction with respect to realizers in this way? Well, now we need to come up with some meta theorems or some criteria that justify that definition, so that people in other communities, such as in numerics, are ready to adapt that definition for their purpose. And the justification that I'm going to give here are two closer properties, namely whenever we have a xi name, and remember we already defined what it means to be a xi name. When we have a xi name of an element and a realizer f that transforms xi elements to epsilon elements, then um, it must at least be defined on all xi names of x. So that's part of this requirement, right? So whenever we have an element which is not part of the domain, then um, the, the observation is kind of empty. But whenever we have an argument which is a xi name of some element of the domain, then um, the classical definition says that the function value must again be a name, a realizer of that infinite sequence. And so in a sense, this means in particular that these definitions preserve computability. So when small f is computable and the argument x is computable, has a computable xi name, then also the value f of x is again computable, namely computed by the epsilon name returned by the realizer. So that this is indeed a reasonable definition. And the second property that justifies our definition as reasonable is closer under composition of computable functions. So let's suppose that f is a xi epsilon realizer of this multifunction, and G is similarly a realizer of that multifunction G. Then the composition of the two multifunctions, as you may recall, that how we've defined that, then the composition admits a realizer, namely the composition of the two realizers is the realizer of the composition of the two functions and multifunctions. So in particular, um, um, computable multifunctions, uh, functions that have computable realizers are closed under composition also in this general setting. So these are both generalizations from what we've already known and seen in the real case, where we've seen that computable functions are closed under composition. And when we plug a computable argument into a computable function, then the value will again be computable. So this is also justification for this yellow definition to be reasonable. So we're going to use that in the sequel. Um, and now we want to compare different representations, different encodings. Remember, we did already compare the three, actually four encodings for real numbers previously, and we proved them, we established them to be equivalent. And that was part of the justification for them to be reasonable. But also recall that they were only non-uniformly equivalent. Uh, Non-uniform, remember, means fixing a real number, then it is computable with respect to either both, all three, or with respect to none of these encodings. A different story is being able to convert one encoding to another, and that turned out to be simply wrong for some of these cases. Okay, so comparing different notions of computability by comparing different ways of encoding, by comparing different representations. That's a crucial property. So we should formalize and define what it means to convert encodings with respect to one representation to encodings with respect to another one. And this is captured by the following definition, which we call continuous reduction or just reduction for brevity. And let's suppose we have two representations, xi and xi prime. And we say a reduction from xi prime to xi is a realizer, xi prime, xi realizer of the identity. Okay, so let's boil that down, what that means. We call that a realizer of a function is a function between abstract spaces x and x in this case is a mapping between basic spaces, namely between Cantor spaces or between Baire spaces, satisfying this property. And now let's boil down this property for the particular case that we have the identity function. So when f is the identity, we can simply drop that. And when epsilon is xi prime, when epsilon is xi and this is xi prime, then this simply means that we need to compute a function from and to Baire space such that the following property holds. Namely, reduction means to a continuous function, it's called continuous reduction, which satisfy this property. And we swing back and forth. So f here drops because this is the identity. This becomes xi prime, and this becomes xi. And you see, this is exactly what is written here. And for reasons that will become clear later, here we can and do impose equality and not just restriction. Well, we could also impose restriction. Okay, and so this is a definition of reduction. Now let's look back. You know notions of reductions, right? You know about NP completeness and about polynomial time reduction. What's the difference and what's the similarity? Well, polynomial time reduction was defined for discrete decision problems, right? So polynomial time reduction was defined for problems which receive finite uh, binary or integer sequences argument, and where the answer to the problem is just yes and no. Here we have a different setting, and here we're talking about a reduction between functions from basic space to, in this case, the same uh, abstract space X. So this is an important concept, reduction between functions functions between spaces of continuum cardinality. So that's an important kind of generalization. And so let's make sure that this is a reasonable definition again. Why would we consider that as a reasonable definition? Well, in the discrete case, our main criterion was that this should become a pre-order, right? In particular, we wanted it to be reflexive and transitive, not antisymmetric though. So, and this is true for polynomial time reduction. Polynomial time reduction is reflexive and transitive. And also this continuous reduction is reflexive and transitive, as you can easily check, right? So xi is reducible to xi, maybe a realizer of reduction from xi to xi is just the identity, now the identity on basic spaces. And if we have a reduction from this representation to this, and a reduction from this representation to another by such functions on basis spaces, then the composition of these functions on basic spaces actually are realizers, are continuous reductions directly from the first to the last one. So indeed, this is transitive, this is a pre-order. Okay, so that gives some reason to define continuous reduction, and let's now use it and consider some example and investigate in particular the three representations of real numbers that we have uh, obtained here by formalizing the ad hoc notions of computability from the previous chapter. And also let me point out that uh, in the previous chapter, we considered the four notion of computability of real numbers, namely one where there are sequence of rational approximations without error bounds, but we already know that this is incomparable. This is much um, more difficult or actually much easier to compute because it's the same as having Oracle access to the holding problem. So we didn't even try to include that any further here. But how about these three representations of, let's say, the unit interval? Okay, and so here's the answer. The binary representation is reducible to the rational representation. Beta is continuously reducible to rho. What does that mean? Again, let's recall the definition. It means being able, this is an interpretation here with xi prime and xi. It means that there's a translation, a continuous translation on basic spaces, which translates xi prime names into xi names. Let me repeat that. Recall what it means to be a xi name. Xi name is something that gets mapped by the representation to some element x, and we want both to map to the same element. We want to realize basically the identity, right? So what f does, f receives a xi prime name of some x, meaning that xi prime of that element should be x, and f should transfer that name, uh, convert that name to a xi name of the same element, namely when we plug the name, the translated name, translated by f, now into xi, it should return the same element as before the translation. So that's the intuition beyond the reduction. And that's a special case, as of course you know, of this computable translation or continuous translation of a function equipped with represented spaces. It is, after all, the special case where x is equal to y, the spaces are agree, and the function is the identity. And so why is this true? Why can we continuously and actually even computably convert beta names into row names? To this end, simply please recall our proof for equivalence. Namely, we consider the first n elements of that input sequence. So in the previous chapter, we would fix the first element of a computation. And here we consider the first element of that input sequence and observe that this constitute approximation to the real number up to error 2 to the minus n, which is actually a diaretic rational. So what I just argued is actually the second part of the example, namely continuous reduction from binary representation to the dyadic representation, which is this continuous reduction, is basically just what we talked about when we talked about the uniform computability of equivalence of these three notions. Take the first elements, take the corresponding binary, finite binary representation, and that constitutes a dyadic rational approximation up to this error. And also, it is easy to convert from dyadic representation to the rational representation continuously. So we have this reduction uh, basically by replacing or inserting integer powers of 2 at every odd position in the sequence. And this is taking the perspective of the base space to be the bare space, which we can do here for convenience, since we can, of course, code and recode back and forth continuously and computably. So what I've just argued is about this reduction. Less obvious is the converse reduction. This requires, as you may recall, uh, searching the input sequence of numerators and dominators uh, for exponentially many elements, such that this error bound 1 over n becomes 2 to the minus n. So that means we uh, walk through this input sequence in exponentially large steps and thereby accelerate and improve the error bound from 1 over n to 2 to the minus n, and then uh, uh, do some rounding by replacing, in order to replace this uh, integer denominator with a power of 2, integer power of 2 denominator. But this is again, as you can easily verify, a continuous translation now from bare space to bare space. The remaining translations are actually discontinuous, and that's a thing I'd like to emphasize. So it's not possible to continuously translate row names, rational sequence of approximations, into binary names, binary sequence of approximations, nor dyadic sequence of approximations to binary sequence of approximations. Uh, and one way of looking at this is by observing that, or recalling that our proof that whenever a real number is dyadic computable or rationally computable, then it is also binary computable. Our proof would consider separately the case where the real number under consideration is a dyadic rational and would hardcode that dyadic rational. And this is reflected by this, considering different cases, is reflected by a lack of continuous translation, namely whenever the real number under consideration is a dyadic rational, then the translation from, let's say, dyadic names to binary names is discontinuous at that dyadic rational. And in our previous proof, we kind of would remove all dyadic rationals from the domain of the continuous of the translation and that restriction of the translation turned out to be continuous. From a different perspective, yeah, that's exactly the discontinuity here. Consider dyadic rational, let's say 1/2, and then we can again formalize this or fooling process, right, into a discontinuity argument. We construct a sequence of dyadic rational approximation to 1/2, one approximating from below and one approximating from above. And then this is exactly where discontinuity happens, namely from finite initial segments of these sequences will either be mapped to something that begins with 0.0 or something that begins with 0.1. So that's a discontinuity here. And so that means basically we have two equivalent representations. We have a partial order among representations. And so two of them are equivalent, continuously equivalent, rational or dyadic. And the binary is kind of in a sense, the strongest one. One can reduce from the binary to everything else, but not from anything else back to the binary representation. So let's record that now we have seen three different representations for real numbers as formalizing encoding over the base spaces. And these are non-uniformly equivalent, but uniformly only two of them are equivalent. Next, let's look again at these three representations and let's have a look at their domains. And what I'd like to point out is that the domain of the rational representation is not compact, whereas the domain of the other two representations are actually compact. So that's another way of looking or investigating different representations. What are the properties of their domains? And their domains are, of course, subset of the base spaces, subset of Cantor space or subset of Baire space. And that the domain of the binary representation is compact, that's kind of obvious because it's, yeah, actually this is a misleading notation. Actually, every binary sequence that starts with 0 describes a real number between 0 and 1, right? If we allow binary sequences that start with 1, then we can even encode real numbers up to magnitude 2. So, and the set of binary sequences that starts with 0 is, of course, isomorphic to Cantor space itself. It's a compact subset of Cantor space. If we have a sequence of binary sequence that all start with 0, then that sequence admits a converging subsequence. And here it's important that we restrict the codomain of the representation to be the unit interval. So for the binary representation, this is kind of natural. We have to make some efforts to extend that to a representation of the real line. Also observe that if we have the entire real line, so this right, I should point out that all three representations are actually continuous, considered as mapping from base space to the real numbers, namely modifying some the input sequence here at the nth element will affect only the final real number in this encoding by error at most 2 to the minus n, right? So actually this is a Lipschitz continuous mapping. In particular, it's a continuous mapping. And similarly here, modifying element at position n and 2n and n plus 1 by means of this very bond means that the value of this representation as a mapping from Baire or Cantor space to the real numbers will change by at most 1 over n. so that this is again continuity, and similarly here. So all three are continuous, and if we have a continuous function with a compact domain, then of course its image is again compact, which means that the binary representation uh, or any representation of the entire line of real numbers cannot have a compact domain. Let me say that again. A continuous representation with a compact domain must have a compact image, right? That's just classical topology. And therefore, if we want to have a representation of the non-compact entire real line, we need to have a representation with a non-compact domain. Okay, but for now in this slide, let's focus on the compact unit interval as codomain, and therefore we have a chance for continuous representation with compact domain, and the domain of the binary representation is compact, but the name of the domain of the rational representation is not compact. So why is that not compact? Well, because of this condition, right? We can, for instance, multiply both numerator and denominator by some arbitrary large integer and obtain approximation with the very same quality. So we can take any sequence that constitutes a name, a rational name, a row name of a real number, and multiply any two uh, successive elements of that sequence with some large number, and obtain again a row name for the same element. And of course, uh, this this means that the set of names of the single real number is itself not compact, right? Can contain arbitrary large integers, and in particular also the entire domain is not compact. Whereas the domain of the dyadic representation is again compact, and this is due to Koenig's lemma, right? Recall Koenig's lemma for Baire space says subset, closed subset of Baire space is compact if and only if it is its set of finite initial segments is finitely branching. And this is here the case. It's finitely branching, meaning that if we fix the element an, let's say, right, then an plus 1 can have only finitely many possible values. That's a set of children in this tree perspective of a set of finite initial segments. And this is because, crucially, because we restrict to this domain, codomain image 0, 1, because this being codomain 0, 1 means that an must be an integer between 0 and 2 to the n, right? If an is larger than 2 to the n, then this ratio fraction approximating up to error 2 to the minus itself cannot approximate a real number that is less or equal to 1, but only real numbers that are strictly greater than 1. And similarly, if an is less than 0, less than 2 to the less than minus 1, to be fair, uh, then this fraction approximates only something that is strictly negative. So there are only, well, it's exponentially many possible values for the numerator of the nth dyadic approximation, but it's finitely many, from minus 1 via 0, 1, and so on, up to 2 to the n. And that's finite and thus satisfy the condition of Koenig lemma, asserting that the set of finite initial sequences is indeed finitely branching and therefore compact in Baire space. Okay, so that were some already important observations about different topological properties of different encodings of different representation. So all three we consider here were continuous, but not all of them were mutually continuously reducible in this sense that it is some of them it's possible to convert let's say, beta names into row names, but it's impossible to convert row names into beta names, which gave rise to this interesting uh, partial order among the three representations. And another uh, um, criterion, another look we took is by looking at the domains of these representations, exploiting that we're considering here representations of a compact unit interval. If we were looking at the non-compact total real line, then things would look more difficult. Then none of these representations could have compact domain, because continuous representations map compact domains, would map compact domains to compact images. Good, so that's about representations, and next time we're going to capture the results of our comparison into a criterion for which representations are reasonable. Um, so maybe this is the criterion is called admissibility. Representation of a space X is admissible if it satisfies two conditions. And the first condition is that the representation must be continuous, continuous as a mapping from basic space onto surjective, right, onto the space X under consideration. And observe that this first condition is satisfied by all three representations of real numbers we've considered so far. It is easy, though, to construct discontinuous representations, but they will usually be unnatural. But now let's look at the second condition for a representation to be admissible, namely, it should be maximal with respect to continuous reduction among all possible continuous representations. So second condition says if we have another continuous representation, let's call it psi prime, of the same space, then it must be possible to continuously reduce, to continuously convert psi prime names to psi names. Well, you can take or leave that definition, but why is that a good definition? At least for now, let me point out that this definition is actually similar to the notion that you're all aware of and familiar with, namely NP completeness. Recall that NP complete means a problem should be in NP, that's a counterpart to the first condition, and the counterpart to the second condition, every other problem in NP, which is the counterpart to say every other continuous representation, every other problem in NP has a polynomial reduction to that problem. So that's why sometimes being NP complete is also called being maximal in NP among all NP problems with respect to polynomial reduction. So replace this symbol with polynomial reduction, replace representation with discrete decision problem, and replace continuous with NP, then you arrive syntactically and semantically at NP completeness. And so that is maybe for now should suffice as motivation for this definition. It was identified and found actually in 1985 by Klaus Weihrauch and Kreitz. And I will tell you more about this notion and its properties in the next session. So that's for now, that's all. Thanks for your attention and see you next time.